Welcome back to the third part of digital modulation lecture. In this part we will talk about frequency shifting, and in particular our topic is binary frequency shifting. So as usual, binary means we will encode bit by bit. So for 1 we will have a certain frequency f1, and for 0 we will have another frequency f0. So unlike the previous ASK modulation technique where the frequency was fixed, this time frequency will be varied but the amplitude will be fixed. You can see for bit 1 amplitude is AC, for bit 0 amplitude is still AC, but the frequency is different. The first frequency is f1 and the next frequency is f2. Okay, so how can we achieve this technique? Let's say we are encoding our input bit sequence. Let me just erase these things. Okay, so let's say our input bit is 1 0 1 1 0, let's say. So let's say our signal is something like this: 1 0 1 1 0. So if we just multiply it with a signal of frequency f1, then we will get something like this: 0, then a particular frequency, 0, particular frequency, 0. We are getting 0 here because anything multiplied by 0 is 0. Here f1 just indicates the frequency, we have the total cause wave here. So if it is 1, let's say it's 1 volt, then whatever the signal, if the amplitude of the carrier is AC, then AC multiplied by 1 will be this signal. You can see here frequency is f1. Again frequency is f1 in this part as well. Here you can see it's illustrated. So let's say this is our message signal MT. MT is the line coded version of our digital code sequence. So we are multiplying it with an oscillator f1. So whenever our signal was high, let's say this is, I assume, 101. So for 1 we have a carrier signal. For 0 we don't have any carrier because in the input it was 0, 101. And then again for 1 we have another portion of the carrier. Now we are inverting this signal. So inverting means now 1 will be 0 and 0 will be 1. So in this path, in this input, the signal will be something like this: low, 0 volt, 1 volt and 0 volt. Remember one thing, the input sequence is 101. We are inverting this, so now it is 010. So now if we multiply it with a different frequency oscillator, let's say F2 oscillator, then it will be 0, then a different frequency, then 0 again. Now if we add these two, we will get this type of signal. For 1 we have a particular frequency which is high frequency. For 0 we will have low frequency. For 1 we will have another high frequency. In this way we can actually achieve binary frequency shifting. So the process is very simple. At first we want to encode our encode our digital bit sequence by unipolar NRZ. Then we want to pass it into a product modulator, and the input frequency of the carrier is f1, and then it is again inverted and passed to another channel. In that channel the frequency of the oscillator is f2. So we are actually multiplying the direct path by a high frequency for bit 1, and we are multiplying the alternate inverted path by frequency f2, which is a low frequency. Then we are adding these two to achieve our final FSK signal. So here is the amplitude spectrum. You can see there are two different carrier frequencies because we are having two different frequencies, so two different carrier frequencies. So a certain portion of the original spectrum is shifted to low frequency omega c0, and another portion of the carrier signal is transmitted to high frequency omega c1. So advantage is FSK is less susceptible to noise. Of course, if I am doing FM or FSK, it is better than ASK in terms of noise performance. And disadvantage is, as usual, we will need more bandwidth compared to AM. So we will need twice of the bandwidth. In the case of AM, we need only one carrier frequency, but in this case we need two carrier frequencies. So ultimately the bandwidth increases. So how can we detect BFSK? There are basically two ways. In one way, we can actually filter out our necessary portion and then just do envelope detection. You can see, just think of this spectrum having a filter here. So here the filter is tuned to FC1 frequency. So the low frequency signal is filtered out. So this is our input signal, and now we are applying this filter, so the output is this one. In another channel we are using this filter. The same signal, but we are using a different filter. So now the high frequency component is blocked out and the low frequency component is passed. Now we can envelope detection. We can use envelope detection for this signal. So we will get 1 0 1 in this channel. This is our envelope detection signal, and in channel this you will get 0 1 0. So we will get after envelope detection we will get this signal in this channel and this signal in this channel. Then we can do, again we have to do sampling, and after sampling we have to compare. Then by the result of the comparison we can actually take the decision whether it is a 1 bit or 0. Let's say in one path we have this type of signal, and in another path we have this signal. I'm drawing it here, 1 0 1. So in this path it will be 0 1 0 0 1 0. So we have to sample values from here. Then after sampling we have to compare that are they of different we know that this path is our main path and this path is our inverted path. We already know that. So depending on this we will make a comparison, that are they agreeing with this. Let's say if this sample is high, then this sample should be low. If this sample is low, this sample should be high, because they're inverted paths. So if this is matched by comparison, then we can decide whether the bit sequence is 101 or whatever else. Another way is we can also use product modulation. You can see there are two different frequencies here. One frequency is omega c0 and another frequency is omega c1. We can at first multiply it with omega c0 in one channel, and in another channel we can multiply the same signal by omega c1. After that, simply by low pass filtering we can filter out unnecessary portions and reach the same result. These are basically same. We will achieve same results by these two circuits, but in one circuit we are using envelope detection, and in another circuit we are using a product modulation. In the product modulation we always multiply a signal with the same carrier and then actually use the low pass filter. As I have already mentioned this many times in the FM demodulation technique, we are actually taking the same signal and then passing it through to different channels. In one channel we are multiplying it with omega naught carrier, and in another channel we are multiplying it with omega 1 carrier. Then we are just using our low pass filter tuned to particular frequency. Let's say for this case it is omega naught, for this case it is omega 1. After that we are doing the same process. We are sampling the signals as I have mentioned for the ASK, and then we are comparing them to make a decision whether it is a 101 or whatever it is. So there is one type of detection which is envelope detection, another type of detection which is square detection, or simply multiplying the signal by carrier and then filtering out the necessary part. Thank you.